Hi, my name is Tej, and I'm going to talk about the implementation of Coq Record Update, a small library for updating records in Coq. So updating records in Coq is too hard. As a prototypical example, consider this record X with three fields A, B, and C. I'll be using this record as an example throughout the talk. Suppose we want to update one of the fields of X, say the B field. For some generality, I've written this setter in such a way that it takes an entire function, which is given the current value of B and returns a new value. Now, we might not just want to update the field B, but any one of the fields of X. This starts to become painful, and it looks much worse once we have more fields in the record. Coq Record Update is a library which automates this process. With the library, the user just has to write this little bit of boilerplate, this AdaX instance, which lists out the fields of the record once. Then, the user can just use this set function, pass it a record field, like B, and set that field. The focus of this talk will be to explain how the set function is implemented. And the short answer is that it basically is an abuse of type classes. I'll now walk through that implementation in 3 steps: representing the record, constructing a setter using LTAC, and then finally wrapping all of this up in a nice interface. First, we have to represent the record's fields. The way that I do that in the library is with this Ada expansion, which is equivalent to the identity function, but implements the identity function by deconstructing the record into its fields and then reconstructing it from those components. If we look at AdaX, we can observe that it's a prototype for some particular field update set B. The only difference is that set B does something different in the B field. All the other fields are preserved. With that insight, we can look at how we implement a setter using an LTAC function for now. Solve setter will take a record type R and a particular projection proj and return a setter in the style of set B for that projection. And on the right-hand side, I'll give a running example of constructing the setter for the field B in X. The first thing that this LTAC needs to do is look up the Ada expansion. The way that it does that is it first gets the Ada expansion by just type checking underscore as settable R. Coq runs type class resolution and finds the Ada expansion. This LTAC actually needs to look at the syntax of how the settable was constructed. It doesn't want to use it opaquely, so we eval HNF in order to actually produce the expression on the right side. So next, we want to take that B field and substitute something else for it. The way we do that is using the LTAC eval pattern proj construct. This abstracts over where proj appears in the expression, and recall that proj in this specific case is B, and it produces a function of an arbitrary projection. This is almost the setter that we want, but it's a little bit too general. Here, the setter is allowed to update B in terms of the entire record, whereas the setters that we want to use are only past the current value of the field B. We can fix that up with just a little bit of LTAC to specialize this setter. I haven't shown the code for this because it looks complicated, but really it's nothing more than specializing this expression. We want to expose a nice UI for that. The way we do that is via the set function, which is part of this type class setter proj. In order to understand how the set function actually works, we first need to ask what really is a class. This class setter is not too different from a record setter with a single field set, except for one difference. When Coq encounters an expression like set BFX, it needs to type check this by inferring all the implicit arguments. The R and T implicit arguments are easy to infer, just based on the proj, in this case B. The more difficult task is inferring this question setter, which is a value of type setter B. This is the only difference between a class and a record. When Coq encounters question setter, which is a class, it runs type class resolution to fill in that implicit argument, whereas for a record, this would simply fail. The type class resolution sets up a problem like question setter is of type setter B, and then Coq searches for an instance with a search that's essentially eauto using type class instances. Type class instances is just a particular hint database that the type class implementation knows about. And eAuto is just a search through that hint database. If you're familiar with the implementation of type classes in Coq, then you'll know that the actual search is slightly different. It uses something called type classes eAuto. The main difference is just that type classes eAuto is not depth limited, whereas eAuto stops after a certain bound. Normally, using the setter type class would involve writing instances like set b. And when we write instance, what that really desugars to is just writing a definition and then adding a hint for that definition to the type class instance's hint database. Now, of course, we don't want to do that in Coq record update because then we would still have to write a setter for every record and every field in that record. But we don't need to do that because type class instances is just a hint database. So we can add a hint extern to it, which runs solve setter. This causes Coq to run solve setter whenever it encounters a set expression. Because type class instances is just an ordinary hint database, we can add a hint extern to it and run the solve setter LTAC that we saw earlier whenever Coq needs to resolve a setter for a particular projection. Why does that even work? It's because type class instances are not really that different from any other hint database. We can use this trick to plug arbitrary LTAC into whenever Coq needs to type check an expression. While this is a complete implementation, we can do better, in particular by adding some notation as well as catching errors that the user might make. The notation helps a lot by improving the ADA expansions so that they can just be a list of fields, as well as greatly improving the experience of updating fields. One thing that notations can handle is setting fields to constants, which is a very common use case for updating records. Some of the errors that we can catch include getting the order of fields wrong in the ADA expansion. For example, in this record X, A and B happen to have the same type, and if you swap them in the ADA expansion, the implementation will actually set B whenever you try to set A, and vice versa, which would be very bad. The way we catch this error is we run some LTAC to automatically prove that the settable instance, this ADA expansion, is actually the identity function. So once again, the user interface of Coq record update looks like the following. The user writes this ADA expansion, which is just a list of fields, and then we have access to this notation to update records. And here I'm showing an example of just setting the field b to this value lowercase b. You can also see that this notation makes it easy to set multiple fields in the same record in a row. Now, we can do slightly better even than that, with some additional improvements that other people have made. You might have noticed that there's some boilerplate that the user still has to write in the ADA expansion for every record. We can use a plugin to avoid this. The problem without plugins is that there's no API in either LTAC or LTAC2 to look up all the projection functions for a record. A plugin neatly solves this, thanks to a few lines of OCaml code, which Talia Ringer helped me write. We can also add notation for nested updates, thanks to a contribution from Jacob Nielsen. Sometimes we have records whose fields are themselves records. So here's an artificial example with a triply nested record. Suppose we have a foo and we want to update this deeply nested field C. Normally, a solution that you might reach for is lenses. And if you don't know about lenses, that's okay, because we're going to solve the same problem with just Coq record update. If we want to update this nested field, all we need to do is set up settable instances for all the records involved. And then this notation A semicolon B semicolon C refers to that nested field. I'm not going to go into detail on how this feature is implemented, but basically it's just a recursive use of set. So in conclusion, Coq record update is a simple way to add record updates to Coq. I think this is a really nice solution that, while it does require a little bit of boilerplate if you're not willing to use any OCaml code, it adds record updates to Coq with a relatively nice UI without having to add any syntax or hack the compiler directly. This is all user extensible. I also want you to take away from this that you too can abuse type classes. There are lots of fancy things you can do with type classes that result in nice user interfaces. Finally, the library is open source, it's on GitHub, and it's also installable through OPAM. If you use it and have feedback, I'd be happy to hear it. Thank you.